Let me just share this. Way better. Okay, before you start the SUE2, you need to set the environment variables, and I think that's put on the GitHub page. And you basically add the environment variables in .basrc. So along with the SPICE environment variables, you need to set these two environment variables, which is CPP sim home and CPP shared home. So in our case, it'll be the project's 15 VLSI 70 for the core space, or if it's somewhere else, then you have to put it there. And then set the path for all the binaries to be CPP sim shared home bin. Okay. Once this is loaded and all the environment variables are loaded, to start SUE2, you basically type SUE2. Any directory is fine. So once you start that, you're going to get this canvas. Just enlarge this a little bit. Okay, so as you can see, you get an empty canvas with some menu items here. This around here. Some menu items here, like for example, all the files, what you can do with Windows, edit commands, tools. This is one of the important ones. So you can do ngSpice simulation directly from here, or just simply create Netlist. And also all the documents are here. So the SUE2 manual, the ngSpice with CPP primer, which doesn't exactly apply, but it'll still give you some idea on how the ngSpice is used with CPP sim. The recent ngSpice manual as well. So the entire ngSpice 32 manual is here. You can access that. The toolboxes for CPP sim, Hspice Toolbox, Hspc Toolbox, the BSIM4 manual is also here. So you can access if you want to know about the BSIM4 models. All the details are in this manual as well. Then also I added the SCMOS, which is the technology mostly we're going to use to do labs here. So the entire SCMOS design rules is also attached to the library as well. Oops. Okay. All right. So what I'll do is I'll first show you two schematics I already have drawn, how to simulate them, two different ways to simulate them. And then I'll show you how to start one with scratch, start from scratch and show you that. Okay. So let's start with the first one, the INVEX. So there are three panels here. The first panel is actually what's called a schematic panel. So any schematic you want to draw or simulate or anything has to be in this panel. This next two panels are called symbol or icon panels. So any libraries you want to instantiate symbols or icons from, they should be in these two panels basically. And you can choose, and the libraries for these panels are already there in one of the directories, which is there in the GitHub. You can find that it's in the CPP sim home SUE2 SUE and that is selectable by just clicking the left mouse button here, and you can choose which. So let's say, for example, I want to choose the SPICE library and simulate some designs from here, then I can click this and select from there. So MyLib is what we have created for you, for people to experiment or have their own user space library designs here. So I've created like two INVEX1, Inverter X1, HSPC. I'll explain a little bit. And this one, like as I said, these are the symbols I can drag and drop to my schematic. So first, like I said, we're not going to do anything with the schematic. I'm going to just show you how to simulate a schematic two different ways, and then we'll do one from scratch. So let's start with the INVEX one. Now, one of the bugs with LXLE SUE2 is usually you're supposed to click left mouse button For some reason, the tickle has a bug in LXLE only. If you are using this in Ubuntu or any other, so you just click left button. If you are using LXLE, use shift left button. So shift left button and the schematic appears here. And this schematic, like I said, it's already drawn. So there's an inverter drawn with the NMOS, PMOS with all the sizes here. There's input port, there's output port. There are two global pins, one called ground, one called VDD. This is all ready. So the first way we're going to simulate this is by creating a netlist for this and writing a test bench using Spice like we have been doing before. Okay. And to create the netlist, we go to these two items, menu items. So there are two ways to create this netlist. One is called Spice netlist. One is called Spice netlist with top sub. And we want to use that because we want to create a subcircuit of this. So if we click this, it'll ask you, and this is already programmed to be in this directory. So it's cppsim home netlist. So we'll just stick with that. Again, another sort of a bug, or I don't know if it was supposed to be a feature in SUE2, is that if you choose the extension .sp, it keeps adding a .sp on top of whatever you have. So it creates a, so you just select all files and leave it at in xp1. You can see there is already a netlist created, but I'll override that. And you just hit OK. So if there was no error, it will say Spice net listing of cell X1 completed with no errors, and you hit OK. So as you saw that this was created in, so let me go to that library, to that directory here. So that's in my case, it'll be VLSI 15, VLSI T, EDA, cppsim lite, netlist, right? So you go here and you see there is a file called invex1.sp. So if you open this, you'll see that there is a dot subcircuit which is created with a input port, output port, two MOSes with a model SCMOS N and SCMOS P, and the library files. I'll show that in the test bench real quickly. And this is it. This is a subcircuit. There's a dot end added to it. Again, there's a bug in the SUE2, but it doesn't affect your simulation. So either you can delete it or just leave it as it is. Okay. So that's your subcircuit, which is in the netlist directory. Now in cppsim, most of the, you can run your simulation anywhere you want. But in cppsim environment, it is in the cppsim home, and there is a directory called simruns. And if you see the simruns, it has the libraries, like, you know, the libraries we selected from here. You see cppsim modules, Spice, miscellaneous example, GMSK, and all that. So those libraries are here as directories. So in our case, it was mylib. So we go to mylib, and this is, you either manually create it or SUE2 can automatically create it, and I'll show that in a little while how. So here I already have a folder called invex1, and I already have a test bench called tv invex1.sp. So I'll just open that and show you what that file is. So you can see it's a standard Spice netlist. So the first one is the title of this the netlist, and then the first Spice command is a .lib, and this is the model file for the MOS transistor I'm using. And this is the SCMOS model libraries, which is you know, referred to in this particular path here. So it has all the models already pre-placed in the ngSpice directory, so you don't have to do that. And it has three corners: nominal, fast, fast, and slow. So we're going to use the nominal corner first. So that's your library file. And then we include this SP file, which we just saw. So you see, this is the file which was created by SUE2. So we include that. So which means that the subcircuit is included right now, but we have to instantiate it. So we instantiate it, we call it xin, in, out, we give the port name, and we call the subcircuit name, which was called invex1 in that subcircuit, right? And then we give all the different Spice directive, like temperature 25. We define a parameter called vsupply 5 volts. We define two globals because there are two, if you see in this Spice netlist, there are two global parameters, VDD ground, which are not ports. So you have to define that as globals and attach the supply and ground to it. So the ground should be a 0 actually. I have to put that here. Okay, so define the VDD and supply as ground. Then I have put a load of 10 femtofarad at the output of the inverter. I've given a supply to the VDD supply and the parameter V supply, which is 5 volts here. And I should also put the ground here as well. GND to 0 and just a DC value of 0 volts, 0.0 volts. So it's basically taking a 0 volt supply and because in SPICE 0 is the global ground. So if you have defined any other thing, actually if you define GND, it automatically defines I think as 0, but just to be safe, apply that. Okay. Then I am applying a clock pulse of 10 nanosecond pulse width, rise time, and this the syntax for all this, you can always go to the doc and ngSpice manual, and that you can search for, like for example, here I can go Control F pulse, and you'll see here voltage source pulse here. You can click that, and you can see here what is the syntax for doing pulse. And that's the beauty of writing your test bench in SPICE itself, because you have the entire SPICE at your disposal. Whereas if you do your test bench in SUE2, then you're kind of limited to what are the devices available in this devices here and in SPICE, and you can see there's not much here. Okay, so write your test bench in SPICE. That's always much more powerful. And then you give some options for simulation for tightening the tolerance and all that. You can eliminate all this. It'll just default to some values, which is typically okay. And here I have given the transient that 20 nanosecond simulated for 20 nanosecond, because that's the period I've chosen here. And I've also chosen to do a DC operating point. Okay. So that's my test bench for testing this. So all I have to do is do ngSpice TB underscore invex1 and ignore these unrecognized parameters because they're just not supported in ngSpice, which is fine. These are BSIM parameters. And, you run them. Okay, so I guess you don't need it. So forget about adding that. I think it's automatically, once you define a ground as global, it's automatically 0. So don't have to add that. Okay, so it ran it. And if I want to plot, let's say, the input, and I showed you a trick of offsetting them in the same plot. So since it's a 5 volt, I'll add like 5.5 maybe, and then V of out. And you can see here, that's your input, the red one, and that's your output. And you can see the fall time is faster than the rise time because, it's the same size PMOS as an NMOS, and obviously the mobility is 3 to 4 times slower for the PMOS. And, you can do all sorts of measurement, like you want to do the rise time, fall time, you can calculate and do all that as well. Okay. So this is how you use SUE2 to do your simulation by generating a subcircuit and simulating. Okay. Now, another method I'll show you, which uses what's called the Hspc Toolbox inside CPP-Sim. Now, Hspc Toolbox, it's like an intermediate language used to write test benches. And the document is here, and that's written by Mike Perot as well, who created the CPP-Sim Toolbox. So if you go to the doc, you'll see a HSPC manual here. So here it explains you what is the command format for creating the test bench in HSPC. Okay, so this allows you to write some very sophisticated test bench in very simple format. So next I'm going to show you how to simulate directly from SUE doing that. Okay, so I created another because these symbols here don't have what's called the geoparameter. So I created another schematic. So that's called invex1 underscore HSPC. So if I click this, you'll see that, and when I create the schematic, I'll show you what's the difference between the two symbols. So again, the schematic is already created. All we have to do is simulate it, same sort of global symbols and everything. But now what we're going to do is we're going to use the ngSpice from the SUE2 environment itself. But before you use that, you have to set it up. And that's set up in the same simruns directory. So you know how we went to simruns mylib. So in the simruns mylib, you'll see there is already a folder called invex1_hspc. So if I go here to sim hspc, and you have to create this test bench, and this is the .hspc file. Here you can have the hspc command or the spice commands, either one of them. If you can write everything as spice commands like before. So you can see I've actually written the spice commands. I have the same library format. I've commented out the hspc tools for now, because it'll take a little bit time to understand what the geoparameters are, what source and drain area is. So for now, you can just do like you're doing the spice simulation. So you put all the spice directives like your library, your temperature, your supply voltages, your global nodes, your loads, um, same way like we did before, the clock pulses, your options, your transient operating point, and so on. And there's a lot more to it, but we'll just keep it simple for now. So once you have created the HSPC file, you can simulate this directly from SUE2, and you go Tools, ngSpice Simulations, okay? And you can see this sim file here. Uh, it basically found this file from this location because it just looks in this location. So if you have a cell name called invex1 hspc, it's going to go into the simruns directory mylib invex1 hspc. If it finds a .hspc file, it'll actually show up here, and you can actually edit it directly from here. But since our environment has set the editor to be Vim, it'll actually pop up in the same window where you started your SUE2. So if I click this, it'll actually edit in this window here. You can see the same HSPC file also pop up here. Okay, so you can do any edits you want to do here and then quit. Don't do Control-C here because it'll kill your session otherwise. And then you can either just do a netlist only. So let's do a netlist only. So if you just do a netlist, it's created the netlist in the same directory here. So if I do ls, you'll see it's created a netlist called netlist.ngsim. And you see here the netlist is only the netlist of the subcircuit, right? Now, if I do netlist plus HSPC, and let's look here, you'll see there is a simrun.sp. If you open that, you'll see that it has created the entire spice netlist now. It has created the subcircuit. Actually, it is not the subcircuit, it is just instantiated all the MOS transistors here, the .lib file, temperature, and all that. And the whole thing is ready to actually simulate. Now you can actually just simulate it right here. You can do ngSpice simrun.sp and do it like before, run it and plot V in, V out and all that, just like before, right? You can do that, or you can actually run it straight from here as well. So if you run it here, it runs the whole thing. It says done. It says where it created the file, which is here. Uh, and it runs it in what's called batch mode. In a batch mode, it instead of you entering the interactive mode, it just runs it and puts all the output in this simrun.raw file. Okay. And this one, you can directly open it in ngSpice as well. So you open ngSpice and you say load ng, simrun.raw, simrun.raw. Okay, and that's it. You don't have to simulate anymore. Now you can just do a plot of all those signals and print or whatever you want to do, and it'll plot all those values as well. So there are different ways, because in CPP Sim there used to be a viewer called CPP Sim View. We kind of have eliminated that because it just takes a lot of resources, and It's not really necessary for doing simple sims. So this is the second way of doing the simulation. So essentially what it does is it takes your netlist from SUE2 from here, this netlist, and then it takes your HSPC file, this test.hspc file, and creates one, because Spice will not understand this HSPC. That's a custom language created by Mike Perot. So that Spice is not going to understand. So what Mike does is he has another script which takes this plus takes this ngsim netlist and creates a final SP file which has everything in it. It has all the transistors, all the test resources, all the library files, everything in it. Okay, so this is the second way of doing it. Okay, now let's get to how we are going to create something from scratch. Let's say I want to do the same inverter design now. So in SUE2, in order to, before you do like, okay, so maybe what I'll do is let me close this. So let me exit this and we'll start again. SUE2, start again. Now you can't do a new schematic right away. It'll say error library, blah, blah, blah. Basically what it means is I have to first select a schematic. So I created a test, which is basically just a bogus schematic. Oh no, not a bogus one, just some voltage divider. You can select any one of them. So shift left key, any one of them. After you select that, then you can create a new schematic. So it says new, same bug here. If you select .su, it does a .su does it twice. So select this all files here, give a file name. So let's say I wanted to give testing test su, test underscore su. Okay, and just say save. So you can see there's a new canvas and I can see a new file name here. Okay, so let's say I want to do the same inverter again. So from the Spice, there are different MOS icons here. They're different types. We're going to choose the, you can see there's a SCMOS N, SCMOS N4, SCMOS N4 Geo, and so on. So we are going to do let's do the first version where we are just using to netlist it out and do a Spice simulation. Okay. So let's choose for that. Don't choose the geo versions because it has something what's called a geo, which your Spice is going to complain. So just choose SCMOS N4. N means 4 means it's 4 terminal where the bulk is also a terminal. If you choose this, then it's a 3 terminal. Bulk is automatically grounded or VDD for PMOS. So always, let's always choose 4. So shift left key, same thing here. Again, if you're using it in anywhere else than LXLE, like if you have your own Ubuntu setup or anything like that, then just click left button, no shift left key. Okay, so shift left key, it'll bring the device in here and you can place it here. Then let's choose a, and already has some default values. You can see 0.6, 0.4, which is already hard coded into it. Now let's choose a PMOS 4. So SCMOS 4, left click, shift left click, and it brings in a 4. Okay, and then you have a lot of edit terminals here, how to add a wire. You can see everything has a shortcut, like wire is W, text is T, line is a L, arc is a, and so on, flipping and all that stuff. So if I want to do full screen, I press F and I can start wiring them now. So I press wire, connect the drains together, the gates together, a little bit wire to put the ports, put one wire to, and each time you have to just keep pressing wire, it just cancels it. And that's, maybe there's a way around it. I'm not familiar with it. Now you can choose the global symbols. So if you choose the global, again, shift left key, it brings in a global. So you can put one global here and you can just copy the same global to the VDD and use the R button to rotate it. Oh, doesn't rotate it. Let's say R. Okay, so you click it and say R, it will rotate it. Wire it to this, and then bulk is also a terminal because we chose a 4-terminal device. So you can connect, we'll connect the bulk to the source as well. Same thing for the NMOS, connect the ground, and then put Input pin, shift left key again, input pin, shift left key again, output P, and okay, so these are just generic terminals. They don't have any names in it. So let's give some names. So let's keep this in like before, out, and call this VDD, call this GND, and this moved. Okay, that's it. Our schematic is done. Okay, schematic is done. You can do a save, and you can see there is a M sign here, just shows M and not saved. So that tells you it's not saved. So save it. That's it, you're done. Okay, so now let's say we want to create a netlist. So we go to tools, create a netlist with top sub. Again, like I said, choose all star because otherwise it's going to add a .sp after that, and netlist file name. So we'll keep it test_SUE and do a save and say completed with no errors. Okay, let's go to the netlist directory and see if that's the case. So if I go to cd dot netlist, I think one more netlist. Yeah, so if you go here, oh, sorry, I don't know how this got selected. So let's put it in the netlist directory. Test_C. So yeah, so you can store it in any directory, but just keep it in the netlist directory. So yeah, you can see now there is a Spice netlist called test_do.sp. Okay, so let's go back to our simruns directory, and here I'm going to create another directory called test_SUE. Okay, and I know my test bench is exactly the same as the previous one, so I'm just going to copy it from the previous one. I'll call it div same file, so tb_invox1.sp. So let's see if we have to change something. So library, obviously we keep something. This one, obviously we want to call our new netlist test2_sp, and in Vim, if you didn't know, there's a great feature. If your cursor is on the file name, if you want to know if that's you haven't made any mistake in typing, you do Control W and F, Control W and F, and it'll actually open that file, split it, and so that way you know you haven't made any mistake writing that file name, and you can also see the file name, and then you quit by doing Shift Q out of it. So this one, obviously, this is called, what is it called? Test_SUE, right? That's the name. So we have to change this to test_SUE. That's the subcircuit name. We keep everything else same, right? And then we just compile, run it, and just Spice. Okay, same errors, and run it. And let's say we do the same plot. Okay, so you can see the input output. Obviously, it's exactly the same circuit, and you can see it being simulated with this thing. And one thing I just wanted to say is that if you want to create a netlist with using HSPC, where you want to use a geo parameter, use the SCN4geo and P4geo so that you have the geo parameters as well. Okay, so that's it. I think that should cover at least the basics of how to do the simulations in using SUE2 and ngSpice.